Hello everyone and welcome to our YouTube channel. In this video we are going to see resistors in parallel. Remember we have seen Ohm's law and resistors in series. So let us begin. If you missed it, you can check the description section of this video and have the link there. So let us begin. So this is a resistor. Why do we call this circuit to be a circuit in parallel? This is simply because the same voltage drop across each resistor. That is, if my source voltage is equals to 220 volts. Please excuse me, let me take my white pen. If the source voltage is equals to 220 volts, then here will be 220 volts, here will be 220 volts, here will be 220 volts. The PD drop across all the resistors will be the same. Isn't that awesome? So you want to connect your houses now. You see, if you use it in parallel, all the appliances will have the same voltage and you can manage it, right? Okay, let us see how to work with this. Now the law that we know on current electricity to work with to calculate voltage and current is simply Ohm's law. And Ohm's law simply states that the voltage across a conductor is directly proportional to the current flowing through that conductor. That is, V is equals to Ri, as earlier stated. And from there we see that I is equals to V on R, as earlier stated. Is it okay that I divided here by arrow and I'm having I alone here to be V on arrow? I'm just written it up there. Isn't that awesome? Okay, well, now what we will do is that since we know that the same voltage is here, so if the voltage is Vi does not consider, let me say the voltage is V1, then here we will be having V1, here we'll be having V1, here we'll also be having V1, same voltage drop across each resistor. Then another thing is that the current leaving this battery, by the way, the longest terminal is the positive terminal and the short terminal is the negative terminal. So the conventional current will be flowing in this direction. I can call it I1. If that current flows and comes up there, up here, it comes here now at this junction, it will, let me call the junction A. It will be either going this way or going this way or going this way, right? Let us say the current leaving the battery is simply I, please, not I1. We already have something there that I would like to call R1. Please. Okay, thanks. So we are just calling this one to be V. So we are just calling this one to be V and this one to be I. Then now the current, when the current comes here, you'll be having multiple paths to flow. This is the current coming up. If it comes this another wire, it can comes down here, we call it I1. It will go this other part of it will go, we call it I2, and part of it will go here to, we call it I3. And that part will come down here as I3, and this one will be coming here as I2, and this one will be coming up as I1. They will be coming and they will come at this other junction B, and they will flow all through as I, and then it will come back here as the I that was leaving the battery, and the cycle continues. That is, energy is conserved. So for this to happen, so at junction A and B, then we'll be having that at junction A and B, I'm saying at junction A and junction B, oops, let me take the red ink. So we are saying that junction A so at junction A and junction B, right, you'll be having that I1 will be having the I which is entering have to be equal to the current that are leaving the junction. That is, I have to be equal to I1 plus I2 plus I3. Similarly, at junction B, the current which is coming into the junction is I1 plus I2 plus I3, and that has to be equal to the current leaving the junction, which has to be equal to I, right? So from this equation, it's the same thing, that the current leaving the junction have to be equal to the current entering the junction for energy to be conserved. So after that, we can now say that we are having the relationship that I is equals to I1 plus I2 plus I3, and I can go ahead and box this equation. Like this. Oops. So I can go ahead and box the equation. So very important for resistors in parallel. Very, very important. So this is the formula. You have to master it, please. Okay, now from Ohm's law, current is voltage over resistance. So now the voltage leaving the circuit, we will now look the current. We want to know the current leaving the circuit, right? To know the current leaving the circuit, we need the voltage and the total or the equivalent resistance of this, because Ohm's law is having a single value of resistor. So to apply Ohm's law, we need a single resistance, and to know the current leaving this circuit, we need to know a certain resistor. We have to bring a resistor which is equivalent to the R1, R2, R3, because before we can apply Ohm's law. Ohm's law is talking of a single resistance. I repeat, we need a resistance that is equivalent to these three before we can apply Ohm's law and know the total current flowing through this circuit. So if I call that resistance to be R equivalence, then the current which is leaving will simply be what? V on R equivalence, and that has to be equals to I1 plus I2 plus I3. So the current is V over R equivalent have to be equals to the other current, which will be what? V1 on R1 plus V2 on R2 plus V3 on R3. Right? I've summed all the currents, and what you have to know again is that the same voltage is through all of these resistors. I said it earlier. If the voltage is 220 volts, then the voltage will be same across all of them. So it implies V equals to V1 equals to V2 and equals to V3. Right? So from there, let me say we take a new page. I have V over R equivalence is equals to V1 over R1 plus V2 over R2 plus V3 over R3. So we are saying that V is equals to V1 is equals to V2 is equals to V3 for resistors in parallel. For resistors in parallel, that is the case. So if I replace everything as V, so we're having V on R equivalence have to be equal to V on R1 plus V on R2 plus V on R3. And from here I can divide all through by V, so that if I divide this one by V, I multiply by 1 over V in both sides. I multiply by 1 over V, 1 over V, 1 over V. You see that this V will just be going. So we'll be left with 1 over R equivalence is equals to 1 on R1 plus 1 on R2 plus 1 on R3. So each time resistors are connected in parallel, then the 1 over the equivalent resistance will be 1 over R1 plus 1 over R2 plus 1 over R3. Please master this formula. Very, very important. So this is the second formula unboxing. So you should make sure you put this formula in your head. So this is a formula like this. So you have to master this formula and this other one for current. The two conditions here is that the current leaving the junction equals to the current entering the junction, and the same voltage is across all the resistors provided they are in parallel. Is it clear? So we can see how to work an example so that I should let the concept be very, very clear. So I would like to say, let us say we have R1 to be 2 ohms, R2 to be 4 ohms, R3 to be 6 ohms. We now want to look for the equivalent resistance in this circuit. So the equivalent resistance R will be equals to, we know that 1 on the equivalent resistance will be equals to 1 on R1 plus 1 on R2 plus 1 on R3. We are having 3 resistors. If there were 4, we'll be having plus 1 on R4. If there were 5, plus 1 on R5, and so on and so forth. Right. So now, if we substitute, we'll have 1 over R equivalence to be equals to 1 over 2 ohms plus 1 over 4 ohms plus 1 over 6 ohms. Okay, now what is that? I will look for the LCM, and the LCM of 2, 4, 6 is 24. or 12 will go. So we'll be having 12 is the LCM, and 12 dividing by 2, so it will be 12 ohms, so ohms cube, right? So 12 ohms cube dividing by 2 ohms will be having 6 ohms square. 12 ohms divided by 4 ohms will be having 3 ohms. 3 ohms times 1 will be having plus 3 ohms square plus 2 ohms square, right? So we will then now say that our 1 over R equivalence will be equals to 6 plus 3 plus 2, which is what? 6 plus 3 plus 2. 6 plus 3 plus 2 will be having 11 ohms square over 12. We're having 1 over R equivalence will be equals to 11 ohms square over 12 ohms cube. So I can invert the fraction. So we're having R equivalence over 1 will be equals to 12 ohm cube over 11 ohm square, and R equivalence over 1 is simply R equivalence, and ohm cube and ohm square can cancel, so we'll be having 12 ohms over 11, and 12 on 11 is 1 point something. I would have my calculator here. Is 1 point something, so let us say 1 point something, yeah, like that. So this is the equivalent resistance. The equivalent resistance is 1 point something in this our circuit. Now what you have to know is that when resistors are in parallel, the equivalent resistance is less than the smallest among the resistors. Here we were having 6, 4 and 2. Our equivalent is what? 1 point something. It's not up to 2. So this is how you know whether you have done it correct or wrong. Your equivalent resistance should be less than the smallest value of each resistor. So I hope you have tried and have something, so you can take on the description section of this video. You will video part 2 where we will go detailedly and find another expression on this. So by the way, you will need to do some screenshots. So this is resistors in parallel. You can take a screenshot, and this is what we did here. So thanks for watching. You are watching from the African Center of Excellence, and any tech problem you have, you can submit on the comment section of this video. We'll see how to get to you as soon as possible, and you can also contact us through our email address that will be displayed on the screen, and you can still get to me throughout. On the description section you will still find the email address, and you can contact it each time you have a problem in science, math, physics, chemistry and the rest. So thanks for watching once more, and have a great day. Presented to you by Muhammadu Idris.